Hello and welcome to Chapter 14. Chapter 14 we're going to be going over correlation and regression. Before we begin, here's a slide about the homework that is due. Please make note of it, and you'll probably get some help with the homework through this PowerPoint presentation. So in Chapter 14 we're going to be going over talking about data, specifically when it comes to regression and correlation. We're also going to be looking at scatter plots, and then we're going to be looking at correlation itself and regression. Now, the book goes really deep in with regression, and there's a lot to regression. There are some things we are definitely going to talk about with regression, but the majority of them we are going to have information on, but not going to be tested on any of it. So everything I talk about today will be used going forward for the purposes of the class, but just know that regression itself is a whole other kind of beast, and there's a lot to it. But we're just going to understand how to calculate regression that many of you probably seen before, and we're going to understand what it means, and that's about as far as we're going to go. We're not going to go into actually hypothesis testing and confidence intervals within regression itself. Okay? So the first thing we're going to talk about in 14.1 is data. So when you have quantitative response variable, it's always going to be a dependent variable when you have a response, right? So if someone responds to something, it's a response, right? It's dependent upon what you said that they're going to answer to it. And just opposite that, explanatory variable would be your independent variable. Now, when we deal with correlation by itself, these two factors, doesn't matter if you interchange x and y on correlation, because the strength of association will still be the same, whether it's positive or negative. The strength will still be there. However, when we're looking at regression, the response versus explanatory variable is very important. You know, this is where we have to chart things on our x-axis and our y-axis within our graph. So that is where it becomes extremely important, is when we get to regression. Not so much about the correlation, but definitely the regression part. Historically important public health data set used to illustrate techniques was Dahl of 1955. This data set looked at cigarette smoking and lung cancer rates per mortality of 100,000. So we'll see here in this next slide here this actual data. So here you have your country, so we can look at USA, and we have cigarette consumption in 1930, and then lung cancer rates 1930 per 100,000, and then it has 11 other countries there. So as you can see, in order to get lung cancer here, for this example, we have our explanatory variable, which is smoking. Smoking causes lung cancer, so lung cancer is dependent upon smoking, and your y. And as you can kind of look at it, you know, just from the numbers, the more you smoke, the more likely chance you're going to develop lung cancer. This is important when we start looking at the scatter plot of this. So when you actually plot these points here, so you can see this part right here is the USA one, and you have your x and y variable, and this is where it's plotted on the chart. So down here, in this little corner, this is, I believe, like 6, and it's going to be just over 200, so we can go back and look. So 230, so that's Iceland. You can see the same thing here, right? 236, and that's the Iceland mark. So this is where it's plotted on a scatter plot. Now, when we inspect scatter plots, there's some things we need to think about and look at. One thing is form. Can the relation be described within a straight line or some other type of line? Direction. Do the points tend upward or downward? The strength of association. Do points adhere closely to an imaginary trend line? Outliers. Are there any outliers? Is there any striking deviations from the overall pattern? So when we judge correlation strength refers to the degree to which points adhere to a trend line. The eye is not a good judge. I know a lot of us will look at a plot and say, oh, there's a correlation there. Well, we can't always say that. And truly, unless we run true correlations, we always want to say association. So there's one of those vocabulary words that some people might get very nitpicky about, is the difference between correlation and association. So just know, in order to have a strong correlation, you have to actually run a correlation example, and it just proves the association that there is there. The top plot appears, so on the next one, next slide here, there's a top plot and a bottom one, and when you look at these different plots, when you look at these plots, you can maybe draw a line there, and maybe draw a line like that through, but like which one of these is actually a stronger association or has a more positive association or correlation to it? And the answer is these are exactly the same plots. It's just the scaling. That's all it is, right? The scatter plots are the same data with different axes. It's difficult to determine the correlation strength visually. You can't really tell visually, so this is why we have to run tests to actually determine where the line is here. So correlation. Correlation coefficient uses R. It quantifies the linear relationship between with a number between -1 and 1. You'll probably see this again. So remember that R is always going to be between -1 and 1. When all points fall on a line with an upward slope, R equals 1. When all data points fall on a line with a downward slope, R is going to equal -1. When data points trend upward, R is positive. When data points tend downward, R is negative. The closer R is to 1 or -1, the stronger the correlation is. So here's an example of this. So here, the very top picture, we see our line go straight up. This is a perfect positive correlation where R equals 1. This is right next to it is a perfect negative correlation right here, where R equals -1. Here we have our line here too, very similar. It's a strong positive correlation where R equals 9, and right here to the right of it is a moderate positive correlation where R equals 5. So you can see as they get more scattered, your line is not as straight upward or downward. So this one goes down and this one's going down. So this is where we look at the association. If the line is going upward, it's positive. If it's going downward, it's negative. And depending on how close all the points are to each other is testing the correlation to the line that we're looking at. So here we go, we're going to calculate R. So when you calculate R, the formula is R is equal to 1 over n minus 1 times the sum of zx, zy. So zx is xi minus x bar over the standard deviation of x, and xy is yi minus y bar divided by the standard deviation of y. These will look very similar. This is what we used when we did z formulas. Correlation coefficient tracks the degrees to which x and y go together. Recall that z-scores quantify the amount a value lies above or below its mean in the standard deviation units. When a z-score for x and y track the same direction, their products are positive and R is positive, and vice versa. If it's negative, then it's a negative association. So this is where this is how we calculate our R value, and we get our z of x and z of y. So I'm just going to show this, and then the next video we're going to go into more detail about actually calculating this. So this would be our illustrative example where we had the cigarette consumption and the lung cancer. So here's the USA, here's your X, and here's your Y. And I'm going to go into next video and go over this in a lot more detail